we want to find the max and min of f of x, y, z equals x squared times y squared times z squared, subject to x squared plus y squared plus z squared equals 1. So we're going to do this using Lagrange multipliers. So we want to find the gradient of f and set it equal to lambda times the gradient of g. G is just going to be the constraint equation, moving the 1 over to the left. And when we take the derivative with respect to x, f turns into 2x y squared z squared, and then lambda times gradient g is just 2 lambda x. And then partial of f with respect to y is 2x squared y z squared equals 2 lambda y. Partial of f with respect to z, 2x squared y squared z, and that's going to equal 2 lambda z. And so we want to make sure that whatever x, y, and z we find, that x squared plus y squared plus z squared equals 1 is satisfied. Now let's look at the minimum value. For this one, you just want to use common sense. We're multiplying x squared, y squared, and z squared. We know that this is always going to be greater than or equal to 0, no matter what real number x, y, and z are. So the smallest it could be is 0. Now, can we find x, y, and z that satisfies the constraint and makes this thing 0? The answer is yes. I can choose, for example, I can choose x to be 1, y to be 0, z to be 0. 1 is satisfied, and then we have 1 times 0, that's also 0. So clearly 0 is going to be the minimum, and there's many ways to do it. You could set, so you can have like x is 1, y is 1, 0, z is 0. X is 0, y is 1, z is 0, etc. Okay. Now let's actually find the maximum value. So for the maximum value, we do want to solve this, the Lagrange multiplier system of equations here. So the first thing to notice is that I have a 2 for all of these guys. So I could just, get rid of that. That's step 1. Step 2, I can get rid of the x right here, the y, and the z. So when I do that, I end up with this. Y squared z squared equals lambda. X squared z squared equals lambda. X squared y squared equals lambda. So from the first two equations, these are all equal to lambda, so you can just set them equal to each other. So if you set 1 and 2 equal to each other, we get y squared z squared equals x squared z squared. And here, I forgot to mention that we're assuming that x, y, and z are not equal to 0, and lambda also is not equal to 0. Because if it is, then we'll go back to the minimum, because that would make x squared, y squared, z squared 0, and that's the minimum. So we want to get the maximum. That means they cannot be 0. Okay, now when we set the first two equations equal to each other, we can cancel out the z squares because z is not equal to 0, and we're allowed to divide by something that is not equal to 0. That means that we get y squared is equal to x squared, and if we take the square root of both sides, we get the absolute value of y is equal to the absolute value of x. Similarly, if you set the second and third equation equal to each other, we can divide both sides by the x squared, take the square root, and get the absolute value of z is equal to the absolute value of y. So basically what you have is that all of these guys are going to be equal. So then when I plug it into the constraint, so remember the constraint was x squared plus y squared plus z squared equals 1. If they're all equal, that means that, x squared is equal to y squared is equal to z squared if you just square everything. So then I could just, instead of writing y squared, I could just write x squared. Instead of writing z squared, I could write x squared. And that means we get 3x squared is 1, x squared is 1/3. So that's what we have over here. And so we could take, well, I guess, you can find what x is equal to, y is equal to, z is equal to, but we're interested in just the maximum value. So if x squared is equal to 1/3, y squared is 1/3, z squared is 1/3. And then when we plug it back to our f of x, y, z, which was equal to x squared, y squared, z squared, replace everything by 1/3, we get 1/3 cubed, which is 1/27. And so this is going to be the maximum.